Hello, 1324 students. I'm going to talk about section 5.2, the fact that there are two different kinds of compound interest. I'm going to give you some typical test questions, and I'm going to use some formulas that don't look like the ones in the book, but the ones in our book don't look like the formulas most people on the planet use. So you go right along and use the book's notation. That's the one they're using in my math lab. Think of this as an alternative version in case it makes a little more sense. Okay? All right. So the common formula for compound interest is that the amount in the account is equal to the principal times 1 plus r over n raised to the nt, where by a of t, we mean that's the amount in the account as a function of time. Time has to be in years. Everything in this context and for simple interest was originally phrased in terms of years. So if you had to talk about months, remember you had to use fractions of years, right? Okay, so P is the principal. Notice that principal could be written as A at time t equal to 0. The initial amount. R is the APR, which is the annual percentage rate of interest. Annual means yearly. N is what, now this is N that everybody else uses. Your book changes it up. But N usually means the compounding rate, which means the number of times per year that an account is compounded, which here means it's increased because you're multiplying it by a number greater than 1. Okay, so do you want your money compounded if it's in a savings account? Yes. Do you want your money compounded if it's in a credit card account? Not so much. You might not, but the bank that holds the credit card wants that. That's their investment, so they want that amount to go up every time that a month goes by and your balance gets multiplied by a number greater than 1. And of course, T is time in years. So, typical test question. Suppose your aunt left you $10,000. So you have $10,000 to invest over the next 20 years. You're wondering what would be a good place to sock that away. Should you invest it in account A or account B, where the terms for account A are that in account A, the APR is 5.14%. In account B, some alternative, the APR is only 5.11%, 5.11%. But there, they're compounding daily. That means every day they're multiplying your balance by a number greater than 1. Daily means every day. How many days are there in a year? Right? That tells you that N in that case will be equal to 365. The number of times they're compounding your account is 365. The interest rate R would be written as 0.0511. And over in account A, here they were only doing quarterly compounding. That means compounding every quarter. Every season, right? Every quarter of a year. So that gives us that there are 4 compoundings per month, a year, excuse me, n is equal to 4. All right, so here are some examples of plugging these terms into a formula. A good idea when you're doing one of these is to write down the formula you're using in letters, the literal formula, and then substitute in the exact values. Notice here how I'm starting to use the calculator notation to remind myself of all those good habits that you need to have. You need, when you want 10,000 for the principal multiplied by this quantity, you have to write 10,000 times, literally times, the quantity 1 plus the R is the 0.0514 divided by 4. If you have these graphing calculators, you can just enter that. You don't have to figure out what that is, write it down, try to put it back into the calculator and mess that up because of that human transmission error, right? just you have to plug it all in. Raised to the, and you could actually just type in 4 times 20, n times t. So notice that's an r and that's an n. Up here is another n. Okay. Students often get this mixed up. Okay, well, versus account B. What changes? So in blue here I have the terms for account A when r was equal to this with quarterly compounding. Not much changes over here, except the r is now 0.0511 and the n, because it was compounded daily, is 365. Okay, that gets raised to 365 times 20, 365 days in a year, right? Okay, so you could just press enter and compare the amounts. But let's say you just want to, you're wondering, when does one of these accounts, maybe that investment takes off versus the other, at what point? So replacing the 20 in here and the 20 in here by x, putting this one into y1 and this one into y2, you could do that, right? Let me just remind you what that looks like. So you want to compare these things. So you go to y1. And notice that when your formulas get long enough, you sometimes have to use this arrow to go further to the right. Okay, you can eventually see it all. It'll still be in there. Notice the profuse use of parentheses. There is a reason for that. Okay, you got to make sure that the calculator understands that you wanted 4 times x in the parentheses, all that to be in the exponent. All right, and back over here, the base of the exponential expression, that whole base is inside parentheses. All right, so here's the base of it. Here's the exponent. We've got parentheses around both when dealing with a calculator, right? So you could just graph. And what do you get? There's compounding quarterly, and then there's compounding daily. Oh, they look exactly the same. So to get to the brass tacks of things rather quickly, you can go to table and find in there the row where x, which is time here, right, is equal to 20. So if we highlight that, we can see, well, at first it looks like it's just saying 27,772, like we have here. I have the camera over here, I need to move that. Okay. First, that's what it looks like. But if you actually put the cursor over that number, you get more detail. So I wanted to point that out to you. Put the cursor over it, and you can get into the fine print. Okay, account A has $27,772.22. Well, it had something like 21 something something that had to be rounded up. So you always would have to round to the nearest cent, unless it's specified to round to the nearest dollar in MyMathLab, something like that. Okay, versus account B with compounding daily. Slightly different APR. So you get everything out to the nearest penny, and the conclusion of all those questions, which one has the greater return and by how much. Account B will be better by, and once you've rounded both of these to the nearest penny, then you take the difference and you get this one's better by $13.26. Well, that's pretty close. That's why the graph wasn't very helpful. So go into the details using table. All right, so now both of those were just compounding when you have where n, the compounding rate is a finite number of times per year. But there is another type of compounding called continuous compounding. Okay. Suppose we had a third option, an account C, where you had continuous compounding. What does this mean? Well, I have a little blurb up here to help explain that to you, what's going on there mathematically. Continuous does not mean daily. That's, first of all, common error students in 1324 make, so you don't make that mistake. I'm double checking you guys can see this. I think so. Yeah. Sorry about the glare. Let's see if I can get you out of there. Let's put the glare over there. Okay. Right. Okay. So continuous compounding. That means that the number of times you're compounding per year has been let to go off to infinity. Okay? You're compounding infinitely many times, so it's infinite compounding. Now, if you take the expression 1 plus 1 over n raised to the n, and you let n get larger and larger and larger, you're going to find that this actually levels out onto this value 2.71828182846 ... And this number actually became famous for a bunch of other things, so it gets called E for Euler, the guy who started to point out all kinds of mathematical things that are very interesting about this number. This was in the 1730s. So not only does this expression go to this fixed number, but if you take that 1 plus r over n, now that looks like our compound interest formula, raised to the n, and raise that whole thing to the t power. Now you notice that this part here is the same thing as 1 plus r over n raised to the nt, right? Because a power raised to a power means you multiply the exponents. All right, so if we take the limit of that as n goes off to infinity, we're going to get this function, e to the rt. And that's what gives us this formula that gets called the PERT formula. So that's what it looks like it says. You see right here? Okay. So if you let n go off to infinity, then you're infinitely compounding, and we have a completely different expression involving an exponential function base e, which is why in chapter 2 you were asked to consider and think about exponential functions, right? Okay, so this is where p is the principal, as always, and r is the APR, as it was here, and t is in years. So in this situation where we have the $10,000 to invest 10,000 times, now you need to know about the e to the button in here. Hopefully you learned about that in chapter 2, but just as a reminder, there are two functions over here sharing this button. ln is what it says in white, and if you use second function, ln, excuse me, let's get out here. So if you have second function, ln, you get e to the, so for example, e to the 0 equals, you should know the answer to that. After chapter 2, yes, it equals 1. Okay, so you're going to use that e to the x button in this section 5.2. So e raised to the 0.0511 times, and you could just put the number 20 in here and answer this one question. Or you could put it in x and graph it as well. One of these accounts A, B, and C look like when they're graphed together. Exactly like accounts A and B did when they were graphed together. In other words, the results are too close to each other to see anything using the graph. So going off to a table, and we get a third column. All right, that is giving us the values for Y3. And putting the cursor over that value when t is equal to 20 gives us $27,787.47, which is much better than even account C. Much better than C by $1.99. Not that much better. So that's kind of interesting. Notice that this was using the same APR, 5.11%. But instead of compounding just 365 times a year, we're compounding infinitely many times a year. And so compounding, after a certain point, the compounding rate doesn't have that great of an effect. Difference in interest rate usually is the biggest factor.